In this work, we propose a method that delivers realistic garment models from real-world images, regardless of garment shape or deformation. While modeling people wearing tight-fitting clothing has made great strides in recent years, loose-fitting clothing remains a challenge. Existing approaches either rely on mesh templates with limited generality, or produce models expressed in terms of 3D point clouds or as a single watertight mesh that tightly binds the body and garment together, neither of which is easy to integrate into downstream applications. To overcome these limitations, we propose a fitting method that leverages shape and deformation priors trained on synthetic data to recover realistic 3D garment mesh from in-the-wild images. Our approach employs implicit sewing patterns ISP model as the shape prior for the garment in its rest state. ISP is an implicit generative model that represents garments using a set of individual 2D panels and associated 3D surfaces. We add to ISP a deformation model that captures potentially large deformations, conditioned on normals estimated from input image of the target garment. The deformations are learned from synthetic mesh data featuring loose clothing. Using the trained models, we design a two-stage fitting process to recover the 3D garment from in-the-wild images. More specifically, given an image of clothed people, we first estimate the normal of the target garment and the SMPL body parameters beta, theta, which are used to compute the body part segmentation and position maps. The maximum coverage garment shape is then skinned to closely fit to the body. Leveraging pixel-aligned image features, our deformation model predicts occupancy maps and position maps, where the former defines the garment geometry and the latter encodes large deformations. The 3D garment mesh is recovered from the 2D occupancy and position maps using ISP and further refined with our proposed fitting process. For practical reasons, the range of garment materials, external forces, and body motions present in the training data is limited. As a result, the trained model can produce inaccurate results when presented within the wild images. To remedy this, and to leverage the deformation prior captured by the network, we refine the result by minimizing a loss function with respect to the parameters of the pre-trained deformation model. This loss is designed to promote a good match between the garment mesh and image observations. Minimizing it with respect to the deformation parameters yields a mesh whose overall shape matches the input image. However, since neural networks tend to learn low-frequency functions, the result might be too smooth. To recover fine surface details, we perform a refinement step by minimizing the same loss directly with respect to the coordinates of the garment mesh vertices. This generates realistic local details, such as wrinkles on the surface. In this fitting process, we do not require external 3D annotations, but only the normal estimation of the target garment. Compared with the state-of-the-art methods that produce results closely adhered to the body, our method can recover the garment mesh faithful to the input image. As demonstrated by these reconstruction from in-the-wild images, our method can produce realistic 3D meshes with fine details across a wide range of garment types, from tight-fitting attire to more relaxed and flowing outfits. Notably, our approach not only accurately recovers the garment geometry, but also provides models that can be directly used by downstream applications, such as animation and simulation.